Have you ever wondered what the heck we're doing here? Hello, everybody. You ready for this? Have you ever wondered what the heck we're even doing here? What it is that makes us solid, causing walls to give us a hard time? Why and how our bodies convince our minds to make certain choices, or vice versa? But ultimately, how these impulses rule our actions and consequently our lives. All of these questions and more will be answered by delving into the central science and beginning to understand why it all matters. Chemistry is, simply put, the study of the properties of materials and the changes that those materials undergo. Rapidly appearing before you is the most simplistic of the elements, hydrogen. The elements make up the building blocks of all material we experience each day, and there are currently 118 known elements, but many are much more prevalent than others. These elements are also commonly referred to as atoms. Everything you touch, feel, and the walls that you walk into each and every day are nearly infinite combinations of the elements we will be introducing throughout this series. The elements themselves are made up of even smaller constituents known as subatomic particles: the protons, neutrons, and electrons. These three specific particles are what all physical matter consists of. As shown, the nucleus makes up the center of an element. This nucleus cluster contains the protons and the neutrons. These particles, which reside within the nucleus, are commonly referred to as nucleons. Hydrogen only contains a proton and no neutron. But additional protons and neutrons in bigger atoms would sit alongside this proton clumped together as the nucleus of an atom. For simplicity, before we dive too deeply into chemistry, a proton can be thought of as a positively charged sphere. A neutron is a sphere with no net charge. The proton and the neutron have generally the same amount of mass. The electron is much more elusive. It is extremely small compared to the other two and has a net negative charge. The electron can be experienced as either a particle or a wave, but for now, it will also be denoted as a sphere, the one with negative charge. As you can see here, a proton is nearly 2,000 times more massive than an electron. If we assume that the mass is directly related to the volume, the size difference would look something like this. In a hydrogen atom, the conventional thought is that there is one proton and an orbiting electron. The proton sits in the center, the nucleus, and the electron orbits this mass. However, this is not a proper representation of an electron as we now understand it. The electron does not orbit the nucleus as planets orbit a star. Instead, an electron provides an electric potential field which resides around the nucleus, forming an orbital that is not like any orbital we conceptualize around the word itself, but alternately something more like a negatively charged electron cloud which emerges around the nucleus. It is best to no longer think about electrons as orbiting, like orbiting planets, but instead conceptualize them as standing waves, for example, as a guitar string vibrates. Once plucked, a guitar string continues to vibrate back and forth and back and forth. It continues to return to its original state and then moves in the opposite direction. There are points that vibrate to the most extreme amplitudes on the wave, and there are points that do not move at all and remain stationary. This is exactly the way electrons can be conceptualized, but they do not begin to resemble this until they complicate further and move into higher electron orbital energy levels. As shown, there's one electron in the atom's surrounding electron field. This electron may reside at any point within the electron field at any time. The truth is that the electron can reside anywhere in space-time at any time. The electron field is the most probable location for it. Don't concern yourself with this thought just yet. The one positive proton in the nucleus balances out the one negative electron, and the net charge on the atom is 0. Let's get a little more complicated. This is helium appearing before you, number 2 on the periodic table. The nucleus contains 2 protons and 2 neutrons. How, you might ask? How are 2 positive particles that all common sense and our understanding of electromagnetism dictates do not want to have anything to do with each other, sticking so close together? Enter the strong nuclear force.